Not all expressions possess a closed analytic integral that can be obtained through symbolic integration techniques. And so numerical integration can be used in these cases to plot the antiderivative of these expressions using a software package like Mathematica. Now in this video, I'm not using numerical integration to obtain the area or the sign value of the area between the curve and the horizontal axis. What I want to do is to use numerical integration to plot the antiderivative of some given expression. So it's the plot of the antiderivative that I'm after, given that numerical symbolic techniques may not be available for a particular expression. Now, some expressions don't have a closed analytic expression for their antiderivative. This is one of them. Okay, it is possible to find an object, but it's very complex and difficult to plot. It has an imaginary part to it and so on. So it's a fair bit of interpretation involved, but there's no easy symbolic antiderivative for this expression. Okay, now this problem occurs in general relativity when we want to find an expression that relates the radial coordinate of some object to its proper time. Okay, so the proper time is the antiderivative, the integral of this object here, plus some constant. Now this is not easily anti-differentiated using symbolic methods. And so we need to use numerical methods for this. And this will be the subject of a future video, but not today's one. Today's one is an introductory video using Mathematica to plot the antiderivative of some expression. I'm just going to use some simple cases here. But we can use numerical integration to generate a plot of the required antiderivative over some given or restricted domain. Now to demonstrate this, let's look at a couple of simple examples such as 2x, which has an antiderivative of the form x squared plus c. Now generally, we are concerned with finding an antiderivative for which the constant c is 0. Okay, so let's use this to find the plot of the antiderivative of 2x over the domain 2 to 4. Okay, the antiderivative, of course, will be x squared. So we input the following into the software, into the program. A is 2, the lower integration limit. B is 4, the upper integration limit. And we're going to use n equals 20. So we're going to produce 20 ordered pairs, which can then be plotted. We'll do this from a table. So the table we'll give the table a name, capital T, for instance, and we'll call up the function table. And we're going to use this combination here between these parentheses here, these braces, not parentheses, braces, sorry. Between these braces, we have the horizontal coordinate being produced here, and then the vertical coordinate being produced here. All right. Both of these are being summed over I from 0 to n. So this produces the horizontal coordinate, as I said before, lower interval, upper interval, and n lot of segments. We're going to integrate the antiderivative here. Integrate the derivative here of x squared is 2x to find the antiderivative. And the key thing here I'll be explaining throughout this video is this value here. I'm not exactly clear on the role of the value, but it plays an important part. Okay, but together this bit here, n integrate in the square brackets here, produces the vertical coordinate. This bit here produces the horizontal coordinate. So this is a table of ordered pairs, which can then be plotted. Now the ordered pairs that are output from this program, which I'll show you shortly, is these ordered pairs here. And then we can plot those, a list plot. Each of these will plot as a dot. Okay, we're going to have an axis origin. We'll set that to 0, 0. We put in a frame and we'll label them. Frame, sorry, is false in this case. I'm just going to use axes. So it looks like something like this. So the antiderivative of 2x, the numerical antiderivative of 2x over the interval x2 to 4 is this one here. There's 20 points here, n is 20. Plotted domain x, in this case from 2 to 4, vertical coordinate. Now this is the exact plot of y equals x squared, if you like, or the exact plot of x squared over 2 to 4. You can see they're both the same. If we ask the program then to plot them together on the single plot, then we will have clearly the two completely and totally overlap. Okay, so we know we have the correct solution because we're able to compare this with the exact solution in this case. All right, now to perhaps show you that, if I go here and I'm going to open up this is going to be fun. Yeah, the program won't let me do it. What a nuisance. I'll do it that way then. All right. Be difficult if you want. Okay, so here, clear all means clear all the variables from memory. I'm now going to input a equals 2, b equals 4, n equals 20. I've given my table a name, T5 in this case. Out come the points. Now, let's list plot those points. There we go, 20 of them. You can see that looks like x squared plotted from x is 2 to x is 4. Okay, so the exact plot itself, x squared plotted from 2 to 4, here it is. And then next stage is simply to ask Mathematica to combine the two into a single plot. And when I do that, you can see they perfectly overlap each other. Okay, all right, let's go back to where we were. All right, so that's that one. So using Mathematica, the following procedure will numerically integrate the expression f dash of z and generates plot over the interval z from a to b. Okay, so first step one is to set a, the lower interval, lower endpoint, b, the upper endpoint, and how many dots do you want, how many intervals. Sometimes it's better to have more, increases your confidence in the end result. Okay, the form of the table, you then give the table a name, capital T in this case I did, table, and input this data here. Okay, notice the 0 here is very important. When you don't have 0, you're going to have troubles, and I'll show you that later on. I times b minus a, because then if you don't have 0 here, they won't overlap. Okay, when we saw earlier, they overlapped for that reason. We're going to see later on this video there's an exception here. I runs from 0 to n, and then we do list plot. Okay, now let's use this procedure to find the plot of the antiderivative of 3z squared over the domain 20 to 40. Z goes from 20 to 40. Input the following: a is 20, lower limit; b is 40, upper limit; n equals 10, which can only need 10 points here. Write out our table, t equals table, and then write out exactly this form here. Again, make sure the 0 goes here. Okay, perhaps notice that 3z squared and its antiderivative z cubed are defined at 0. Perhaps that's the reason. I'm not exactly sure what role this plays. If you don't have a 0 there, it causes you problems. Anyway, the output that's returned is this, these ordered pairs here. Okay, and then we can plot those. And I'll show you that plot now. The variable z here. Okay, so here's the list plot of the numerically obtained through numerical integration. We've obtained the points that lie on the antiderivative of 3z squared. Okay, now the antiderivative of 3z squared is z cubed. So plotting that exactly from 20 to 40, we get this, plotting it symbolically, the analytic solution. And then if we ask the program to combine the two plots so we have a single plot that we can compare them, we end up with this here. Okay, beautiful, they exactly match. And so this is the plot of the antiderivative of 3z squared. Okay, next bit. Let's just try this on a different one. Let's use a trigonometric function. So let's use this procedure to find the plot of the antiderivative of cos x, which clearly is sin x, over the domain pi on 2 to 4 pi. No particular reason for choosing that range of values there, that domain, but just for demonstration purposes, I could have chosen any. So we input the following: the lower endpoint of integration is pi on 2, the upper point of integration is 4 pi. I'm going to choose 30 dots this time. The more dots, the better. It sort of fills in. You'll see why shortly. We set up table, again, this form. These ordered pairs here will be plotted once they're obtained. Again, notice the 0 here. Perhaps cos x is defined at x equals 0. I'm not exactly sure what the role this is. The output that returned is this, and then we can list plot it. We'll center the plot by asking the origin of the axis to be set to 0, 0. Just makes the plot more pleasant to look at. and we're just going to have some axes, and we'll label those. Next thing, okay, so the plot of the top left is numerical values for the antiderivative of cos x, while the plot of the top right is that of the analytic integral sine x. So this is the analytic version, the symbolic one, was plotted outright. This is the numerically obtained values using numerical integration, and then plotting the output. Okay, you can clearly see they agree, and when you ask the program to overlap them, they clearly overlap, exactly overlap. So we know that we've attained numerically the correct solution here, which is handy because you imagine if we didn't know what the symbolic solution was, we weren't able to plot sine x for some reason because we didn't know what the antiderivative of cos x is, then it wouldn't matter. This orange graph wouldn't exist here, but we still have these points here plotted. And if we want more points, we simply change the value of n. We can put n as 100, 200, however many points you want to put on there. Okay, now let's use this procedure to find the plot of the antiderivative of 1 on x. Now, we know x is singular at x equals 0. It's not continuous at x equals 0. But we're just going to do it over the domain 2 to 4 where it is continuous. Okay, so we plot the following. A is 2, the lower end point. B is 4, the upper end point. We're going to have n equals 20 points. 20 ordered pairs being produced here to plot. Okay, when we do that, we set up the table as before. The only difference is now, instead of a 0 here, we're now going to put a 1, and that works. Okay, I'll show you that shortly. And if you don't put a 1 there, you won't get the same plot. You'll get something which is parallel to the solution, but not in the same. So putting this 1 here causes them to coincide. Why that is, I'm not sure. So the returned output is this. Okay, we then plot this. Okay, and it's going to look like this. Okay, so plotted the antiderivative from 2 to 4 of 1 on x. Well, the antiderivative of 1 on x is, of course, log x, natural log of x. Okay, and plot the natural log of x is this object here, which is the same as the numerically obtained values for the antiderivative, using the antiderivative. Okay, you can see they're the same. Then ask the program to superimpose the plots, to plot them together on a single plot, and they exactly overlap. The only difference is here, instead of putting a 0 here, and I'll show you that doesn't work, if you put a 1 here, it does work. Okay, now maybe it's something to do with a 1 on x, the original function is singular at x equals 0, not defined, not continuous, x equals 0. Okay, that may be what it is, and so just choose another point, but I've tried other points around it, and it doesn't work until you put 1 in there. I'm not sure why that is. Okay, so we have, anyway, just be aware of that, and to show you that, I was going to get up Mathematica again. Here we are. Let's just go down. Yes, no, not this one. Where has my 1 on x gone? There it is. All right, so again, clear all variables. A is 2. B is 4. N is 20. Here's our table. Notice the 1 in there. There's some values going off the screen here. Sorry about that. Okay, now let's plot these. List plot. There they are. Now the exact plot of log x. There it is. No problems. And then ask Mathematica to show us both together. And you can see they clearly overlap. Now, if I were to go back here and put 0 in here, whoops, didn't like that. Still generated some values. See, it's not making sense now, is it? Look at that. This doesn't change, of course. Natural log x, that's the analytic solution. All right, combining them. Whoa, totally different. Okay, so what I started doing, okay, so 0 clearly doesn't work. Okay, could have something to do with that 1 on x is not defined, x equals 0. All right, why don't I put 0.5 in there? When I do that, okay, it likes that, it's happy with that. plot that, but I still don't have the same solution. And when I come down here, let's just go down here, plot them together. Ooh, parallel, but not the same. Okay, pick a different value. If I pick 1.5, for instance. Okay, let's try that. Yep, I was happy with that. All right. That's not looking the same, is it? Put them together. Nope, just doesn't work. Okay, so any other value but 1, if I put 1 in there now. Okay, let's plot this. Yes, that's better. Keep going down, and they agree. And it won't work unless I put 1 in there. Now, all the other examples I gave you earlier in the video, x was the original function, the derivative, and the antiderivative, or certainly the antiderivative anyway, was defined at x equals 0, z equals 0, whatever I was using. So 0 seemed to be appropriate there, but once you come here, x is not defined at 0, but if you put 1 in there, it all works. I don't know why that is, but you can see clearly it works. Okay, that's just one thing to be aware of. Okay, just be aware of that. Now, let's come back to where we are. Okay, so our new numerical integration method, where the integrand, where the symbolic, the integral is not defined at a value, put 1 instead. Okay, it will work if you put 1 in there. Okay, so again, set up lower interval, lower endpoint, upper endpoint, number of intervals you want. The more just gives you more dots and fills in the plot for you. Table, the ordered pairs being produced here. Just remember here, in this case, well, we were using x, but anyway, in this case, z is not defined at 0. 1 on z is not defined at z equals 0, not continuous at z equals 0. So put a 1 instead. I think that's the reason. That's the best sense I can make of it anyway. Okay, now one more thing. Let's go back to the problem state at the start of this video. There's this one, 1 over the square root of that object there. No easy symbolic closed analytic solution. So numerical integration can still provide us a very good one. Okay, so what I did do, use this new procedure to find the plot of its antiderivative, because remember 1 over x at x equals 0 is not defined. So we're going to put a 1 in here instead. So lower endpoint 2, upper endpoint 4. We'll choose 20 dots, 20 markers, generate our table of ordered pairs, 20 ordered pairs generated from here. The output returned is this. Okay, that we then plot it. I use the label f of x as the antiderivative. All right, now numerically obtained antiderivative and plotted is this one. Okay. The antiderivative, I was able to find an analytic solution and I was able to plot it, so that was just sheer luck, but I was able to get this. But even if I didn't have this, I could be confident, given everything else I've shown you in the video, that this is the correct solution. But anyway, using Mathematica, put them over the top of each other, plot them on the same axes, and I end up with exactly aligned and matching. So even if I didn't have this exact symbolic solution, and I wasn't able to, or if I did and I wasn't able to plot it for some reason, because it was quite a large expression, I can still be confident in this, given all that's gone before it, that this is the correct solution. So long as I remember that I had to use that in that little point there, I had to use a 1 and not a 0. Okay, so our two numerical integration methods are this, that one. Okay, 0 if the antiderivative is defined at x equals 0, let's put 0 in there. If it's not, then put a 1 in there, and it seems to work. Let me just, one more, I was just going to, where was that? Here it is. It turns out, where was it? No, there is a symbolic closed analytic form, this one, and I was able to plot it. here it is, but quite complex. There's this complex number in here. So I was able to plot that and produce this. When I tried the one related to relativity, by putting in the gravitational constant and the mass of the object, and then tried integrating that, I was getting this. When I tried to plot it, it just wouldn't plot. So not much use having a symbolic expression after if you can't plot it. That's what happened. You've got these complex elements of it, this elliptic f function. Okay, that's not what I meant to show you though, but anyway, let's have a look here. In this particular case, numerical solution here, a equals 2, b equals 4, n equals 20. Here's our table. Okay, happy with that. When we plot that, we get this. Okay, luckily enough, I was able to plot the analytic solution, so let's go. There it is. That analytic solution I wasn't able to find for quite a while. I kept trying, but anyway, eventually did work. But anyway, okay, I'm plotting them together. So I can be confident that this numerically obtained solution is correct. Okay, but even if I wasn't able to find this, I could still be, given what's happened before, I could be content that this is correct. Here, notice the 1. Very important, the 1 there, not 0, because x is not defined at 0. This expression is not defined at x equals 0. All right. It asymptotically approaches x equals 0, but it's not defined there. It's not continuous at x equals 0. So you can't. Perhaps that's the reason it's not continuous at x equals 0, so we put a 1 instead. And that might be all it is. That may just be where the program's written. Okay, that's how we go. If I did, for instance, put a 0 there, you'll see. Whoops, I better clear all. That might help. Here we go. Yep. Let's try plotting this. Don't tell me it's going to play now. No, see, doesn't work. The two no longer agree with each other. Let me just try this one more time. Yeah, whereas if I now go back and place a 1 here, okay, let's try all that again. Here we go. And I plot this now. Oh, that did lower it a little bit. And of course, just checking now. Let's just see, will they agree with each other? And of course they do. Okay, so in that case, put a 1 there. All right, that is it. That is the numerical integration method. If it's not defined at x or z equals 0, or whatever the variable is, put a 0 there. If it is defined, if the integral, the antiderivative of this, is defined at z, x, or whatever variable you use equal to 0, then put a 0 there. If it's not, put a 1 there. Okay, that's the process. All right, that's the end of that.